Welcome back, folks. We've always said if you keep coming back, it means you're happy with what you're doing, you're giving us a vote of confidence, and we cannot let it go to waste. So, what we'll do, we'll try to do our level best to give you the next, which is multiplexers. So now, what is a multiplexer? All right, let's start with something a little basic. What I'll do is let's take a switch, a simple switch. Uh, Let me rather do this way. Single pole, one line, double throw, can throw this or that way, or that way. So it's an or situation. You can see if I feed two different inputs here, if I have input 1 and input 2, by simply toggling this switch from position 1 to position 0, okay, if it's in position 1, it's going to allow our, what they do here, our Y depends on what? On where the switch is. If the switch is in position 1, I1 is out, or if the switch is in position 0, I2 will be out. This is the basic concept of multiplexing. Choosing, not exactly choosing, but allowing two or more. Multi, remember, the minimum of multi is 2. It cannot be 1. So 2 or more, what you call this, inputs to be allowed to travel on one path. All right, that is what multiplexing is. I mean, it could also be multiple circuits, being able to select between different between those circuits. Right. So now that is the basic concept of a multiplexer. We could have well, two sounds too shallow or too low to be multi, really, but that is the basic one. We could have a rotary switch in the place of what is going on. Okay, let's suppose we have a rotary switch with so many inputs, and our switch could be toggled from those four positions, between those four positions, could be toggled between, those four positions. It could be in any one of position 1, position 2, position 3, or position 4. There could be more. So if I had multiple inputs, 4 in this case, hence multi, already the suggestion is there that multi. So we've got I1, I2, I3, I4, and all these could be transmitted along that one line. All right, so the concept of multiplexing is taking a lot of inputs and embedding them on what? On each other on a single line. All right, that is our Y output. So it could be either one of those 4 in this case. So, but then look at this. We have a problem here. If it's going to be a person that's going to switch here, then it has to be a very, very, very slow process, right? The inputs should be very, very slow changing inputs, because in the event of typical signals, uh, to use a switch here will be impractical because it will be way, way too slow. So this is only for purpose of explanation, because for a system that is switching times are also very, very critical. All right, so also remember that from switching from one to two, two to three, three to four, it has to be done. The transfer rate is very critical. It's very important. All right. So now what I'm going to do is we're going to say let's go more practical and rather select digital. Have digital switches instead of these analog type switch. All right. What I'm going to do now, we're going to say, okay, what if we're the system with multiple inputs as we've shown, as we've indicated? Okay, inputs, input 1, input 2, all the way up to input n. We could have as many inputs as possible, and then these inputs here are going to what? Are going to literally be wired to a multiplexer. Okay, and then the multiplexer is going to what? You've seen what the multiplexer does. It will take all This will be N, that will be 1, 2, but there could be many of them, and this is going to give us one output. All right, so this is basically our multiplexer. Okay, handshaking with a what? All right, for going forward, we're going to call the max, or max for short. All right, we're going to call it the max. All right, so what it means here, an example is in the a lot of parallel circuits being converted into what? Into a serial circuit. These could be parallel inputs, all right, and then they're being converted into what? Into serial outputs. Obviously, they're going to come one after the other. All right, so that will be another job of a multiplexer is to what? Is to convert from parallel to serial. All right, data from parallel to serial. All right, so now a simple example is if you think of a phone network. All right, a phone network. You cannot have practically, if you could have, your address book could be full, ne? I mean that there's so many people that you talk to. Now imagine a scenario where if you're going to if you know our communications goes for on the what? Well, the old times it used to go on the lines, ne? We have satellite communication now. But let's suppose the whole system with the what? With the telephone lines. Imagine that all the people that you're going to talk to are going to need to have a line, a dedicated line that comes from your house to their house. So just imagine how many lines you're going to need to have. Imagine where these people live. They all live in different directions and from where you are. Now imagine that each of them had a line that leaves your house going to theirs. And they also had lines that come into their house from the other people, because they obviously don't talk to you alone, you know. So imagine scenarios where the lines are crisscrossing, because now it will be a nightmare in the skies, right? That will be a nightmare in the skies. So what do we then do? We then come with multiplexing, where one line carries a lot of phone calls. You could be talking, in the neighbor could be talking to someone else and whatever, and that all data is then through one line, where to be split in front there. Right, that we'll later talk about the concept of demultiplexing, which is where the signals are split back into the original what? Into their original either they were singular, and then they were put into what? They were put into they will put in a serial format. Now they're gonna have to be converted back to parallel. Now the parallel to serial converter would have been your multiplexer, and then when you take it back to from serial to parallel, that will be a demultiplexer. Like we said, we're gonna look at that at a later stage. So now the whole concept. Let's take the simplest multiplexer that we have. So that will be a 2 input, because obviously we'll have one selector switch. Now what we're going to do is we're going to do digital selection. Now we're going to do digital selection, because obviously we've seen now that analog switch did not work. So we're going to go into the what? Into the faster concepts of what? Of digital selection. And obviously now we're going to start thinking of logic functions. Now let's go back and say, how do I select? It means if I have input 1 and input 2, which is the max multiplexer, cannot be, if you want to talk multi, the simplest form of multi is 2, because multi means many. Okay, the simplest form of many is 2. So now what we're going to do is we're going to say, let's start with the 2. It means therefore we're going to use one or the other. When you're introducing gates, at some point I think we're talking about, if you haven't looked at that, we're probably looking at that at the memory elements, and I introduced what I called the OR circuit, and I simply said the OR circuit, the basic OR circuit. If you have 2 and you want one or the other, if you've got 2 inputs in this case, and you want one or the other, you would remember that we had the what? A set of AND gates for control, and then we had an OR gate to decide the one part or the other. So this is what we had when we discussed the OR circuits. The basic OR circuit was our first multiplexer, because we are going to say now this data D0, we are addressing it as address 0, or the other data D1, we could have the 1. I could simply put an inverter on one gate and take our selection and take it from, so this is our selector there. We take our selector, we say if our selector can be on 0, which means let me not do that, let me rather do this. Selector is such that 0 is converted to a 1, okay, through the what? through that AND gate that allows DO through. So that will be, if we have 0 there, we are saying we are going to have out D0, because that 0 is changed to a 1. But if it's a 1, the 1 is changed to a 0 there. That 0 would have closed this gate incidentally, because 0 there locks that gate. It will come out there regardless of what D1 is. But a 1 there will say, what are you? So if this is a 0, the 0 comes through. If it's a 1, 1 and 1 will be what? Will be a 1, so the 1 has come through. So 1 will say, what I say, 0 is choosing. Yes, 0 is choosing, is becoming a 1 there and opening for D0 now, but the 0 is closing there. Now when you have 1, 1 is changed to a 0 via that inverter there, so this is not what? This is going to be off, but then this is going to say, what are you? 0 will come through, or if it's a 1, 1 and 1 will come through, so this will allow through D1. So our output here will depend on where your switch is. So your selector switch is very important. It will determine our output. Well, we do know that probably we could have done it a little bit different this way. We could have said some people prefer to draw it is the same. Some people prefer to draw it with an inverter, with the, even though that one was also an inverter, but other people prefer the symbol, and then it's still the same thing. It means the same thing. All right. So this is basically what we called it previously. We dealt with this and we called it the OR circuit. Now we are saying, oh, our OR circuit is actually what? Our basic. This OR circuit is actually our what? Our basic multiplexer circuit, in the sense that it is the simplest form which has a choice between two. Now the number of inputs, the number of data that can be selected, number of inputs, I'll call them inputs. The number of inputs is going to be given by 2 to the power of n, where this is the number of switches. In this case, with only one selector switch, therefore it allowed what? 2. 2 to the power of 1 is what? Is 2. So it allowed only 2 inputs it through. This is the simplest one, but let's go and look at the next one. Let's say now with 2 switches, what can you do? Alright, maybe I shouldn't have removed that one, but it's fine. You can always go back with the what? You can always, it's a video, so you can always go back and look at it. So now when you have got 2 switches, it means 2 to the power of 2, which is 4. So we'll have 4 possibilities. So meaning, again, in the OR circuit, it can be the 1, the second one, the third one, or the fourth one. So with 2, you can then have, and we know we select with the AND gates in this case. So what's going to happen is you're going to have that, or that, or that. I will let you go straight. All right. Or finally that. So they all go through an OR gate, because literally you're going to choose one of them. All right. You're going to decide which one is coming out through the what? Through our multiplexer. So what we then do is we go on and say we need 2 inverters. Okay. These 2 go there. So 0, 0 is changed to 1, 1, and it allows that data through. Let's call it data 0. Okay. Now 0, 1, 0, 1 will mean 0 from this one, and 1 from the other one will open that one there, and our D1 can come through. Okay, and then as you can see now, the next one will be what? 1, 0, gone too high. I'm not happy with that. These should be straight lines, so I'm using the equipment I'm using. So 0, 1, oh wait, 1 0, yes, 1 0, 1 0 is fine. And then this will allow the third input. These are supposed to be straight lines. I'm trying to make sure I don't take too long. And finally the last one will be 1 1. Direct lines here will open that gate there, so that, okay, we have D4 there. So what then happens is that our Z here depends on which one you chose. All right, so as you can see, this here, if you are both on 0, these selector switches, digital selection, now you can see, because with both of them on what? On, so let's put the truth table here. S1, S0, they could both be off, and our output will be, if they are both off, so this is going to be 0 closing that gate, that's going to be 0 closing that gate and that gate. So it means that only this gate is going to have 1, because the 0 is changed to 1, and that one is going to be 1. Only this gate is going to be have 1s, so only T0 will go through. So 0 0 allow T0 to go through. Okay, then when you've got, oh, what am I doing? When you've got 0 1, it means that this one is on 1, so but the 0 here closes 1, it closes 2. Okay, those two are closed. Now we say 0 1. Now did I count correctly? Let's see. 0 1, the 1 is, okay, the 0 there is closing 1 2. The 1 here is a 0 there is closing that one. So now 0 here is going to be changed to a 1 there, and that one is a 1, so you can see D1 is going to go through. Now when you've got 1 0, the 0 here is closing 1 and 2, so D1 and D4 are out because of 1 and that line there. So that D1 and D4 are out, but the 1 here is being changed to a 0 there and that there, so D0 is also closed out. So what are we left with? We're left with the 1 here coming to the gate of D2, and the 0 is coming there and changed to a 1, and it opens D2, so you can see D2 for that reason will come out. And then obviously now we have 1 1, that 1 changes to a 0 and it closes D1 and D0 out. We are left with the other 2. Now 1, that 1 is changed there and it closes D2 out. So 1 comes there, the other 1 comes there, and D4 is allowed out. Probably the last case I did not do the truth table. So this is basically the truth table of what would happen with the combination of the switches there. Alright, so now availability is also a critical issue when it comes to these multiplexers. So usually in the market you find very readily you will find the first one that we did there, the 2-to-1 multiplexer. Okay, you also find this one here, the 4 inputs 4-to-1 multiplexer. You can find also the 8-to-1 multiplexer. You find the 16-to-1 multiplexer for that matter. All right. So obviously now the 16-to-1 multiplexer would need obviously to have 4 of these. All right. So that you can have the count from 0 to 15. All right. 0 will allow the one through, 1 will allow the other one through until we get to 15. So it allows 16 of them out. So now, however, It is also very important to note that multiplexers can be combined to give you even more. Even though in the market, what's readily available is what? Is the 2 to 1, the 4 to 1, the 8 to 1, and the what? And the 16 to 1. But combinations of these can be made to give you even what? To even give you greater capacity. All right, to give you greater capacity for the multiplexers. Probably with the previous scenario, probably should say maybe with my 2, maybe I skip this part. Some people will find it a little bit disheartening. That with the 2 that we had previously, it was a simple OR gate as we've done it before, the OR, the selector. When we're doing shift registers, left or right, when you're doing counters, up or down and all that, we introduce this selector here, and you said this here is basically our OR circuit, and I've just described it now and said all you do is ensure that the 1 is closed when the other one is open, and vice versa. So here what you have is you basically have, this is what we had, and you said you could choose the 1 D0 or the other one D1. What I didn't do was I did not show that with S on 0 you allow D0, your output will be D0 truth table, and with the S on 1 you allow what? You allow D1. Okay, this is what I did not show, the truth table, and I however remember to do it with this case here, and I said, but I did explain how it works, I just didn't explain the truth table. So as you can see, with one switch you're able to choose only 2 to the power of n to the power of 1 gave you 2. With 2 switches you're able to do 4 to the power of 2 is what? Is 4. So now I will entertain the last one, the very last one, which is our 3 input one, even though yes there's a 4th one, but I expect you I expect the students to also try and do this, because it's not really that difficult. But for purpose of space and everything, I'll just engage my last one. All I did was, now as you can see, this is for people, for it to be visible I have to make the gates big. Now however I'm going to be restricted by the space I have, so I know it's going to be 3 inputs, so I know I expect it to choose between 3 switches, selector switches. So I expect it to what? To go from 2 to the power of 3 from 0 to 7. 1 2 0 1 2 3 4 5 6 and 7, and we know this is all going to go through an OR gate because we are embedding it on the same channel. So now this is going to be that, or that. It's about to rain here, so I hope the noise will not be too much. Let me rather undo this. Let me rather make my gate a little bit big. I can see that I'm gonna have issues, so I'm gonna make a very big OR gate to allow what I'm trying to explain here. Okay, giving us one output. You can choose that one there, choose the next one, choose that one there, choose that one there, choose that one there, choose the other one, that one there, oh, that one there. As you can see, it's an OR gate, so our output can be any one of that. Let me make them long because I need the space in between. As you can see, I'm trying to rush it to not make it, to not take forever with the video. Oh God, my issue is I know what I need to put in there, so I don't want it eating up all the space in front of the gate. All right, now, so now we know we've got 3 switches, 3 selector switches, and hey, this is going to be a problem. So we have 3 inverters for each. Okay, now we have 0, choosing that, as you can see, that's why I said I needed what, and that. So that 0 0 will become 1 1 1 and allow D0 out. And then now the next one will be 0 0 and 1. So that one there is gonna come from direct from that, so the 1 can go straight. Now the next one will be 2. It's all AND gates, so let's rather do the AND gates. This is what I was trying to avoid by doing only 2, but I want to make sure that the information sticks, it sinks in. So this here is 2, so which will mean 0 from this one. So remember, this will allow D1 because 0 0 1. D2 will be 0 1 from that one there. No, I don't like this because I don't like again. A little bit difficult to draw this line up. 0. Okay, that's 0 1 and 0 from that one there. That one there is going to be D3, so it's going to be 0. After the inverter, that one is going to be 1, and that one is going to be 1. So now we're going to have 4, which is going to D4 is going to be 1. This one here. Just missed it. Okay. One, 0, and 0. Can you please complete this, because I think you can see what's going on there. Please complete this so you can see now your input is going to be what. So you go all the way D5, D6 and D7. All I left is 3 of them. Please complete them. You know the count 1 1 0 for the next one. So you can have your truth table S4, S2 and S1, 4 2 1. So it gives you the count. So your truth table is going to be S4, S2 and S1. Complete that, and then all the way up to 1 1 1. Complete this. We're going to look at next part. We're going to look at what, at the applications, but I'm going to break this up because I think this video has become too long. We're going to look at applications. I'll finish this up on the next thing, and then we're going to look at applications. Thank you so much, and ciao.